All right, so looking at equipment and trying to figure out the changes in resistance. We have a weight stack, okay? So all of these plates, gravity's accelerating it down. However, we have this what's called a Kevlar belt. It's a line of force and it's pulling up, okay? So we're gonna start here and we're gonna look at this and we're gonna follow it all the way up around this pulley, okay? This pulley is just moving this belt around here. Now it attaches on this device. Can you zoom in? To this cam. It's called a cam, okay? It changes the resistance, it manipulates the resistance. Okay, then we look at this cam and there's an axis going through it, all right? So weight stack, belt, or line of force, going around a pulley. If you take this off, you can see inside of it and see the pulley coming down, attaching to a cam. On that cam, there's an axis. And if you can get around, when you look at an axis, understand that it doesn't start here and stop on the other side. It's not a piece of metal, and think of it as an infinite line that everything's spinning around, okay? So, weight stack, line of force, cam, axis, all right? Find those things. Then, if we look at, once we introduce movement to this, you can see this, make it lighter, you can see this belt on the cam and where it goes, how it moves as you go through the motion. In this motion, it's going to be concentric spinal flexion, okay? Now, the first thing I want you to look at is this belt, the one that's directly on the cam, not the one that's coming from the weight stack, the one that's directly connected to the cam, in its distance relative to the axis, all right? So go back, find that axis, now find this belt, okay? The simplest way to do it, as we look, what's happening? Is this belt getting pushed farther away from the axis, or is it getting closer to the axis, or is it not changing at all? And what you can see here is the first thing that happens is it's getting pushed slightly farther away, and now it's coming closer. So you can look at it going closer to that axis, or you can look at it coming away from this guide rod. Okay, and you can see how it's going away from the guide rod, this distance getting farther and farther and farther away. As we get into full flexion, it's at its farthest away from the guide rod. If it's farther away from the guide rod, it means it's closer to the axis. Okay? That's probably one of the easiest ways to see if the line of force is getting closer or farther away. You can also measure, okay? And we can look for specific distances to figure out if the moment arm of this scenario is shortening or becoming larger, because the greater the moment arm, the more torque. The less the moment arm, the less torque, if we're keeping this magnitude the same, okay? So, again, weight stack, Kevlar belt, which is your line of force, pulley, Kevlar belt, attaching into the cam, axis. If the line of force gets closer to the axis, the resistance is getting less. If the line of force is getting farther away from the axis, the resistance is increasing. Lighter, closer to the axis, heavier, farther from the axis. So in this scenario, you can see it's getting slightly heavier, and then as we go down into more flexion, it's getting lighter and lighter and lighter and lighter and lighter and lighter until we're all the way down here, where it's at its lightest, or where the moment arm is the shortest, or where the distance between the line of force and the axis is the shortest. Okay, all the same way of saying one thing. And now we'll get into the effort component of this, which is going to be you. So the effort component when analyzing equipment always comes from you. Okay, remember, internal effort is muscle, internal torque, just think muscle. So here the muscle is coming from the user, right? And what you're looking at is where they're pushing into this piece of equipment, okay? Now this one, if you watch the path of motion that occurs, okay, he's spinning around the axis of the machine, okay? So we keep that in mind. Then we look at his direction of force. So if you had to like take a laser and point it the direction he's pushing or pulling, right now this is called an input pad. Okay, we're going to look at these input pads and figure out where he's pushing. Right now his force, here's where his force is going. Okay, now as he goes through the motion, that force is pretty much going to stay 90 degrees to this input pad the entire time. Okay, and if you look at this position, go ahead and eccentric, as you go through this position or this motion, the position of that line of force does not change relative to the axis of the machine. Okay, so you're looking at the user's effort, its line of force, and if the line of force gets closer, this is what it would look like if it got closer to the axis. This is what it would look like if it got farther away from the axis. Okay, so what you can see is as he goes through the motion, if his force stays 90 degrees to this input pad the whole time, it does not change relative to the axis. Okay, and the reason being is this is a fixed lever. Okay, this lever isn't retracting and expanding, it's staying exactly where it is. So the machine offers an effort that stays exactly the same, okay, an effort arm that stays exactly the same relative to this axis. So we have resistance on this side that decreased throughout the range. We had effort that stayed the same throughout the range. So the overall resistance profile in this machine is that resistance drops off or resistance lessens through end range trunk flexion, okay? Which is an important aspect to know relative to tools, because what we know is as we get further into muscle shortening, we get weaker and weaker and weaker, or less able to produce contraction. So this could be a great tool if you want to work in end range of trunk flexion. As they get fatigued, as the muscle gets shortened, the resistance also decreases.